A galaxy is a mind-bogglingly huge thing. For that matter, a star is a mind-bogglingly huge thing. I mean, our own planet is. And there can be billions upon billions of stars in a galaxy, which itself can be hundreds of thousands of light years across. The phrase billions upon billions of stars rolls lightly off the tongue, but it really does take time to make room in one's head for the reality of it all. I remember trying to make sense of this concept during my master's project. Some friends of mine were showing me what they were working on. They were observing these clusters of ultramassive galaxies formed at the very beginning of the universe via the James Webb Space Telescope. I remember looking over one nondescript galaxy after another, staring at each blurry object for only a couple of seconds, despite the fact that each one of those could contain meaning for all I knew. After all, each one contains billions of planets, and each planet is its own little world. Each has its own unique history and idiosyncrasies, worlds where binary stars rise in the sky, or desert worlds, or ocean worlds, or worlds that are made entirely of diamond, or worlds that rain glass for eternity. Were any of those worlds able to sustain life, the sort of life that goes on to build radio telescopes? Were there astronomers currently looking over at the Milky Way at us, wondering the same thing? We can't be sure, of course, but we do know of our own existence, and it has been puzzling our astronomers for millennia. We see a universe filled with a very large number of planets. For us in the Milky Way, it is on the order of 100 billion or so. Presumably, given the principle of mediocrity, some of these planets hold the conditions necessary for the emergence of life. There's no reason to suggest that the phenomenon of intelligent life capable of constructing radio telescopes and spaceships is unique to our planet. Similar conditions, or different solutions entirely, presumably exist in many other star systems, so why would some of them not produce similar outcomes? Moreover, given the vast timescales involved in the formation of our galaxy and its stars, it is overwhelmingly unlikely that any given intelligent civilization would match our current technological level. The emergence of Homo sapiens on Earth could easily have been shifted by, say, a few million years in either direction, if things had gone slightly differently. For instance, say the asteroid impact that wiped out the dinosaurs 66 million years ago had instead occurred 5 million years prior. Apply that to the aliens' analogous event. That would have given our extraterrestrial neighbours a 5 million year head start to colonise the galaxy, or at least to send out probes or radio signals. 5 million years is a blink of an eye in the 13.6 billion year old age of the Milky Way, but it turns out that's more than enough time for a spacefaring civilization to make a significant imprint on the galaxy. Von Neumann famously calculated that it would only take about 1 million years or so to colonise every star system in the galaxy with self-replicating probes. It seems that, by definition, any intelligent civilization would have an inclination to continually expand. And exponential growth necessitates exponential energy growth, which is hard to hide. Freeman Dyson proposed his concept of Dyson spheres or Dyson swarms, these huge megastructures consisting of orbiting satellites that encompass a star, harnessing a significant portion of its power output to meet a spacefaring civilization's energy requirements. This sort of astroengineering project would be visible across interstellar distances, especially due to the periodic dips in brightness and the infrared heavy spectra it would cause. If this seems far-fetched to you, consider the technological advancements humans have undergone in the last few hundred years and where we'll be in the next few hundred years, never mind 5 million years. By maintaining our current upward trajectory and overcoming challenges like climate change, rapid and fully reusable rocketry, and AGI, we will flourish and eventually reach other star systems. So, given our thought experiment here, imagine 5 million years of computation for these technosignatures to crop up, whether radio signals, probes, or Dyson spheres. When we opened our ears in the midst of the 20th century with our fancy radio, infrared, and optical telescopes, you would have expected to hear a cacophony of voices and artifacts of hundreds of intelligent civilizations. And yet, when we did open our ears, we heard nothing. How utterly strange. And it's true, by the way, since the dawn of the SETI program, no reliable or reproducible evidence of intelligent life has been detected or observed anywhere other than Earth. This phenomenon is so confusing, so paradoxical, that it is given a name, Fermi's Paradox. It is named after the physicist Enrico Fermi, who, allegedly exclaimed one day to colleagues, "Where are they?" As in, if the universe is so vast and old, where are all the other intelligent civilizations? Now, there have been many proposed solutions to the Fermi Paradox, ranging from the sobering to the frankly absurd. The paradox relies on an assumption that I've alluded to so far in this episode, the principle of mediocrity, basically that there is nothing significant about humans in the cosmic scheme of things. Or as Stephen Hawking put it, humans are just a chemical scum on the surface of a typical planet that's in orbit around a typical star on the outskirts of a typical galaxy. In the 1960s, 70s and 80s, Carl Sagan and Frank Drake, among others, also popularized this idea, arguing that the evolution of life on Earth, including human beings, was typical, and therefore that the galaxy is teeming with complex life. It was the golden age of SETI, and with the advent of radio technology and space exploration, it was convincing, especially when driven by the numbers argument, the Drake equation, and through raw emotional appeal, often stating that it is arrogant to assume we're rare and special. But as I shall explain, this could not be further from the truth. Consider Hawking's remark again. It is true that we are on a somewhat typical rocky planet of a typical star in the galaxy, but we are far from typical of the matter in the universe. Consider sampling a random 1 light-year by 1 light-year cube of space. The vast majority of the time, you will find yourself in a much colder, darker, and emptier region of space with no scum in sight. Most cubes would be in intergalactic space, where it is so cold that the temperature remains at the unvarying background of 2.7 Kelvin from the faint afterglow of the Big Bang. The nearest star would be so far away that the sky is pitch black. Not even the brightest supernovae would so much as glimmer. That is how big and dark the universe really is. And it is empty, by the way. The density of atoms is below 1 per cubic meter. Almost all of the atoms in intergalactic space are hydrogen or helium, so there's no chemistry. No life could have evolved there, nor any intelligence. And the same story is true for the next cube and the next, or for the next million cubes you examine in any direction. In truth, the universe is mostly vacuum, plus radiation and dark matter. Ordinary matter is only familiar to us because we're made of it, and because of our uncommon position near large concentrations of it. In the grand scheme of things, concentrations of matter such as planets and stars are uncommon isolated phenomena in the universe that are the result of hundreds of millions of years of computation. In other words, they are emergent phenomena stemming from the rules-based system of the laws of physics. That is to say, they emerge after applying our very best theories to the initial state at the Big Bang. But importantly, they do not contain any meaning or any significance because they are governed by these simple, repetitive laws. So, what is significant? Well, consider the set of all physically possible transformations of matter. Some of those, like faster than light travel, never happen because they are forbidden by the laws of physics. Some, like the formation of stars out of primordial hydrogen, happen spontaneously, and the rest, such as arranging carbon atoms into the shape of a tree or converting raw materials into a radio telescope, are possible, but happen only when the requisite knowledge is present. In other words, if you take any physical object, for instance a star system or a grain of sand, many more interesting things can happen when it is manipulated by entities with explanatory knowledge, as in people. A grain of sand might be nudged slowly by a current, or it can be purified, melted, and transformed by people into a microscopic chip of silicon. The solar system might be destroyed when its star explodes as a supernova, or some chemical scum might emerge on a nearby planet and the people there can prevent their own extinction by extending the lifetime of the star, namely by removing some of its mass. Such a project would use many orders of magnitude more energy than humans currently control, but fundamentally it's a simple task that doesn't come anywhere near violating any law of physics. So, with the right knowledge, it could be achieved, and interestingly, it follows that to have an accurate theory of stellar evolution, one must allow for the possibility that nearby life with sufficient knowledge can alter a star's sequence. But this is all to say that the class of physical transformations of matter that could happen spontaneously in the absence of knowledge is negligibly small compared to the class that could be brought about artificially by intelligent beings who wanted those transformations to happen. And so, most of reality is only accessible to those who can create explanatory knowledge. This is the cosmic significance of explanatory knowledge, and hence of people who create it. Here's another example of its importance, and this one really does get me. Say you wanted to know where the coldest place in the universe is. As mentioned earlier, deep space sits at 2.7 degrees above absolute zero. Only very unusual circumstances cause temperatures to dip below that 2.7 Kelvin. Nothing in the universe is known to be colder than about 1 Kelvin, except for a few physics laboratories on Earth. So if you want to explain how an object might possibly cool down to a millionth of a degree above absolute zero, you cannot avoid explaining in detail what people and their knowledge would do. No, yet far from insignificant. Now, I want to further emphasize how significant humans are in the cosmic scheme of things, and therefore how wrong the mediocrity principle is, by briefly turning to the rarity of intelligent life. The mediocrity principle assumes, usually with little or no argument, that the emergence of intelligent, conscious beings like us is an inevitable outcome of evolution. But in reality, it required an improbable combination of astrophysical and geological events and circumstances. Even once it gets going, evolution does not promote the welfare of species or individual organisms. All it does is favour the genes that are best at replicating in the given environment. And by sheer coincidence, environmental pressures continuously favoured larger brains for the last 2 to 3 million years or so, with greater information processing capacities and problem-solving abilities. But compare this to the Mesozoic, where dinosaurs were the dominant terrestrial vertebrate for 165 million years, and as far as we can tell, no intelligence emerged, despite that being a huge amount of computation. But it was simply a time where specialization was rewarded more than large, energy-intensive brains. So overall, I find it difficult to pin down exactly what ingredients are required for life to emerge. Folk usually point to a few dozen of seemingly important quirks of our planet and star system, such as continuously occupying both a galactic and stellar habitable zone, a planet with a low orbital eccentricity and a medium-sized axial tilt, and a strong magnetosphere and plate tectonics, a large moon. Perhaps it's a large nearby gas giant is needed to attract asteroids away from the planet, an appropriate ocean-to-land ratio, an appropriate mass, an appropriate chemistry in the lithosphere and atmosphere, and so on. But we must be careful not to have an anthropocentric bias when analysing Earth's characteristics in too much detail, for there will be idiosyncrasies about every planet in space. What matters most is whether any of Earth's circumstances are not only unusual, but also essential for complex life. I would seriously doubt that there exists only one solution in the universe for producing intelligence. In fact, there are no doubt infinitely many solutions. For instance, I don't think anyone would argue that there exist scenarios where intelligent life could arise around a K-type star instead of a G-type one like our Sun, in a different region of the galaxy, or in a binary system, and so on. As for how likely any of those configurations are, we don't know. There is only so much we can infer from a sample size of 1. But if we remove our anthropocentric bias, then what remains? Like, what are the non-negotiable requirements for life to emerge? I can think of 4. Life cannot emerge without an energy source, right? Whether it's a traditional one like a star, or something more exotic like radioactive decay or tidal heating on a rogue planet. I also think life necessitates an information storage system. For us, that's DNA, but presumably there's other solutions as well. Another non-negotiable requirement would be a high metallicity content in the area. Every organism on Earth is made up of a diverse array of elements, and so I would struggle to see how life could arise from only basic ingredients. Finally, I think for evolution to pay off, it needs a long-term stability on the order of billions of years. So overall, we can identify that any solution for life in the universe requires 1. An energy source, 2. An information storage system, 3. A high metallicity in the area, and 4. Long-term stability. Brilliant. Just to wrap up then, if there's one message I want you taking away from this video, it is the following. There is the commonly held belief of the principle of mediocrity, that humans are insignificant chemical scum in the cosmic scheme of things. But that is a misconception. Whilst humans are physically small and our environment is untypical, we are cosmically significant because of our ability to create explanatory knowledge. We scum are universal explainers and therefore universal constructors, capable of building anything from particle accelerators to floating space stations up in the sky. And that is a really rare thing. We're not perfect, of course, we have our problems, but there will always be problems. And problems are soluble. It's just a matter of gaining the relevant knowledge. And that fills me with infinite optimism for the future. Despite this, I do wonder how many one-planet dead civilizations there are out there. We should be immensely grateful for our consciousness and safeguard it by expanding humanity into the stars and beyond. Thank you very much for listening.